There it goes. Cool. All right, so thank you. Yes, today we're continuing the saga of 10.3. In this, we're doing polar coordinates. We're going to get into a little bit of calculus today. So the main calculus that we're going to be doing is how can we figure out tangent lines for these polar curves. And so I'm here, these are the course video notes, the pre-class notes that I asked my students and everything to do before class. And so you probably already watched these. And last time we did a quick review, kind of how to plot points in polar coordinates and how to plot curves in polar coordinates. And so we never really talked about this page here, where we're getting into how do we do some calculus. That is, in particular, this section, we're interested in calculating out tangent lines or the slopes of tangent lines, things like this. And so this is the main definition and theorem that we need right here. Basically what we're doing is that we're thinking of these polar curves as just parameterized curves. But instead of using a parameter t, we can just think of our parameter or our independent variable here being theta. And so we know the equation, for instance, x equals r cosine theta. And if we have, some curve is given to us in the equation r equals, so for instance, it's good to look at maybe this example down here. So we have some r equals equation, then we can just take that and substitute it in for x, right, into that x equation. And so then we have some equation that only has thetas in it, right? So we just put that, 1 plus 2 cosine theta or something like this in for that r function. And then we multiply by cosine, and there we are. Oh, hey, Alec. He's connecting to audio. Likewise, for y, we could go ahead and do the same sort of thing, but with multiplying by sine. So again, we're thinking of these essentially as parametrized curves, but with our parameter being theta rather than t. And so in that case, we can go ahead and calculate out the slope of a tangent line. So tangent lines are still dy dx, how much our y changes versus how much our x changes. So it's still a rise over run when we talk about tangent lines. But we can go ahead and use this, and we'll formalize kind of why this formula here works in actually 10.2. So that's what, next Wednesday, I believe. We do 8.1 on Monday and then 10.2 on Wednesday. And so we'll talk a little bit about this. But essentially, you can think of it almost kind of the idea is maybe you prove it this way, and you can see how if you treat these derivatives as fractions, and they're really not fractions, but if we abuse this just a little bit, then you can see these d thetas would cancel out, and you're going to get this dy dx sort of deal. And so this is what we're going to be doing. We're going to be taking the derivative of y with respect to theta, of x with respect to theta, and this should be, just take the ratio of those, and that should be our slope of our tangent line, aka the derivative of y with respect to x. I recommend that you don't memorize this bit here. The book has it, and that's kind of why I included it in all of this, and the course video notes and everything, because people see this in the book. But I would just use this equation right here, that you just take the derivative of your y with respect to theta, derivative of x with respect to theta, and then you remember rise over run. So the y's should be on top, the x's should be on bottom. So I see, Alec, you're here. It looks like you're muted, by the way, just an FYI.
Can you hear me now?
Yes, sure can.
Okay, yeah, I had trouble getting in. There wasn't a link on the D2L page that I was click on.
Oh.
And I wonder if maybe some other students are having trouble getting in as well. I finally found it like under a saved setting in my Zoom, but.
Okay. Yeah, I saw Willie's email, and I didn't even check if the link was in there either, but I saw on Piazza someone had asked this, so I responded with the link there. But that's a good point. I don't know if you have a second, and if you want to add the link to D2L, I think that may help a few people as well. But we do have quite a few people in here, as much as maybe we can expect on a Friday after an exam. So yeah, let's see, there's a few chats here going on. Yeah, it's on Piazza right now. Dig into the email to get it. Yeah, so this is good feedback for next week. I'll make sure that that's posted along with our course notes and stuff, I guess. I didn't do a great job about posting those, kind of the exam, and I helped program the exam and stuff like this. That took up quite a bit of time, so I'm sorry I dropped the ball on a few of these other things. Let's see, hard time finding it as well. Yeah, this found an old email. Okay, cool. So yes, next week things will be more back to normal, and I'll make sure to have those posted in several places so that way it's easy to find. Okay, so this right here though is essentially all that's new, all that we really need to add to our 10.3 repertoire, I suppose, in order to finish up the problems. And so let's go ahead, and I guess this is usually where we did some example problems here related to this, and then that was it. So I guess I'll pause for a second and see if there are any questions about this before we get into the new stuff for today. And you may see on the question and answer, again, kind of it's under answered stuff now. I'll maybe post it in the chat as well. Let's see. If you don't have the problems, oh, it's not letting me grab that. Let me put it in the chat here. Oh no, that's the Zoom link. I was just going to post the problems for today in case if you had a hard time finding that. Let me copy here. And under the chat, I will go ahead and paste. There we go. It is also on D2L now, by the way.
Oh, I just tried to do the same thing, so it might be up there twice, but.
Ah, okay. All right, so here we are, 10.3 again. These are the Friday's class notes. I want to start off, we're not going to get right into the tangent line stuff quite yet. This is going to be some stuff that's still kind of on the algebra side for polar, but kind of a different flavor of questions than we went over last time. And then we'll get into calculating out some tangent line stuff and kind of some of the trickier questions that can be asked with that as well. So I'm starting off with this kind of a little bit more conceptual question here. It's a true-false question, and it just asks, do these two polar equations have the same graph, right? And so at a cursory glance, when we look at these things, well, they don't have the same equation. And so, thinking about kind of Cartesian, it seems unlikely that they would have the same graph, but we should double check. And so, okay, why don't we just take a point? I'm going to go ahead and name these things just so I can kind of be very specific. I'm going to call this R1, right? So this is my first curve, and this is going to be R2, my second curve. And so let's go ahead, and I'm just going to choose a point. Let's say, theta equals pi over 6 or something like this. So if I choose theta equals pi over 6 and I plug it into my first curve, right? So I'm going to have sine of, let's see, 2 pi over 6. That's going to be the same thing as pi over 3. So that's going to be root 3 over 2. And so if I was to do a little quick sketch over here, so at the angle pi over 6, so I'm looking in this direction, I have to take root 3 over 2 steps out. So again, root 3 is around like 1.7, divide that by 2, so it's a little under 1. So maybe if this is 1, I go a little under that, and there we go. Okay, let's check about for our second curve here. So if I go ahead and I plug in the same theta value, and I'm looking off in this direction, oops, pi over 6, into my second curve, well, let's see, I'm going to have negative, right? And everything else is the same. So it's going to be negative root 3 over 2. So when I'm looking off in this direction, I'd have to go backwards by root 3 over 2. So you can see, at least for this angle measure, they don't seem to be outputting the same points, right? They seem to have different graphs. However, there's actually a second chance with these polar curves, right? We can see that when we were looking in this pi over 6 direction, we actually moved backwards. So the question has to be asked, well, what if you're looking in this direction here? Sorry, it's lining right up on top of this. Let's go ahead and see if I can just offset it by a little bit. So if I'm looking in this direction, this is almost like a second chance for R2 to actually hit this point, right? Because again, they're going to have the same graphs if they hit all of the same points. So my question is, what happens if I plug in now, instead of pi over 6, this angle right here, if I wanted to go all the way to this, that's going to be 7 pi over 6. So if I was to plug in 7 pi over 6 into my R2, is there a way that I hit that point actually? And so if I go ahead and I plug this in, let's see, I'm going to have negative sine of, let's see, 2 times 7 pi over 6. So that's going to be 7 pi over 3. So if I do 7 pi over 3, I have to think about this. Here's maybe 1 pi over 3, 2 pi over 3, 3 pi over 3, 4, 5, 6, and 7. So, okay, I'm actually kind of back to where I started. I guess I could have just taken off 2 pi from this, right? So that'd be 6 pi over 3 if you wanted to. And so this is going to be negative root 3 over 2. So again, when I'm looking in this 7 pi over 6 direction, this is saying that I need to go backwards root 3 over 2. So when I go backwards, I actually do land exactly on top of this point here. And so we can see that R1 hits this point and R2 hits that same point. And so now I'm a little bit conflicted, right? Because it seemed like at first that they weren't actually giving the same graphs, but now it's a little bit, maybe they do, right? And so I'd like to give you a little bit of a test for this, right? Because this was just one particular point here, right? So one way that you can do this, right, is if they hit all the same points at the same angles, right? But somehow we have to take into this account that if you rotate by 180 degrees and you move backwards, that's kind of like the same thing as going forwards when you were looking in the original direction. So I was looking at pi over 6 originally, and I took steps out in the positive direction. But when I was looking at 7 pi over 6, so I added 180 degrees, or pi radians, notice that going backwards took me to that same point. So the question, and how I'm going to solve this problem here, is that, right, we have to account for 180 degrees and going backwards, right? So going backwards means that instead of going, in the positive radius direction, I'm going to go in the opposite. So I'm going to basically change my r to negative r in order to indicate that I'm moving backwards. Mm-hmm. And then I'm going to change theta to 180 degrees plus my original theta to account for that I'm looking in the opposite direction, right? And so let's go ahead and do that for our R2. So I'm going to say, instead of R2, I'm going to put negative R2. And then let's see, we have negative sine of 2, and instead of theta, I'm doing 180 degrees plus theta. So notice now these negative signs cancel out, and we're going to be left with R. And let's go ahead and distribute this 2. So we'd have 360 plus 2 theta here once I distribute that 2. And I claim that this is actually the same thing as sine of 2 theta here. And anyone have a guess why? Maybe you could type out in the chat or in the Q&A or something like this. Why can I just drop the 360 from the angle measure here? So I'm just going to add a few notes while I wait here. So this is moving backwards and looking in the opposite direction. So that's why we did those 2 things. So yeah, so I now have started to see the answers pour in, and all of them so far that I've seen looks correct, right? That sine is periodic. Likewise, cosine is periodic, right? And so if you were to rotate 360 degrees and then start going, right, you'd get to the exact same spot, right? So it's all about kind of these terminal points and things like this. So it's just essentially that sine is periodic, and every 360 degrees, right, it starts to repeat itself. So that's why you can essentially just drop that 360. And so you can see that this wasn't mapping all of the same points at the exact same time, but if you were to look in the other direction and move backwards, they do actually hit all of the same points, because we were able to transform. Once we did those 2 things, it literally turned our R2 into our R1 equation. And now we see that these things exactly line up. Another way, so I mean, we can cheat since I have graphing here, right? I included a link. Oh yeah, I was looking on how to cook some fish. So yes, this is sine of 2 theta. And I told you guys last time actually that I was going to parametrize this. So I have this parametrized as well. And I think it's just really enjoyable to watch. So let me go ahead. I'm going to click play and just show you what happens when we run the theta through 0 to 2 pi. So let's go ahead and click play. And you can see this point just running around here. And so that's kind of as we look in all of these different directions from 0 to 2 pi, this is how it gets mapped out. And then if we go ahead and we just, I'm going to insert a negative sign here. So a negative sign and nothing else. So you can see it's already started to graph, and they do graph the exact same graph. But now notice when I go ahead and I click play this time, that it's going in the opposite direction. That's essentially all that's changing here. Still very enjoyable to watch. So it doesn't map out, you know, the same points at the exact time, right? It's offset by this 180 degrees essentially, kind of, and you get them by moving backwards. So yes, they do map the exact same points, and that's kind of a tricky sort of question here, because again, it was really looking like it was going to be false initially, but it turns out to be true. Okay, and kind of this leads into something else. I guess maybe I'll pause here and just see if there are any questions or extra things that you'd like me to cover. So yeah, I'll pause for a second, but then I'm getting into another kind of subtle thing about polar that you may not have realized. So again, this is something that, again, the equations look different. If you graph these in Cartesian, you wouldn't expect them to be the same, but in polar, they can be, just because of this fact about moving backwards and looking the opposite direction. Anything you'd like to add, Alec?
Nope, I think you've covered it pretty well.
Okay. Well, I don't see any questions coming in yet. We can always come back to it if you guys get some good questions here. But here's one where I would actually, these ones are all kind of annoying to type in a bunch. So I'm going to switch over to my other computer here shortly. But I'd like to give you guys, 60 seconds, 90 seconds or so. I'd like you to guess kind of the period for some of these types of functions. So right, in polar equations, we're trying to guess the theta interval in which the graph is traced only once, that we get the full graph, but it's traced only once. And this becomes very important later on, as I mentioned here in 10.4, when we're determining arc length and areas, that you want to make sure that you get the entire curve, but you want to make sure that you only get it once, right? If you start graphing it multiple times, or if you start trying to calculate out the arc length and you're tracing it multiple times, right, you're not going to get the right answer, because you're going to get like maybe twice the arc length. Or if you didn't get the entire curve, right, you're not going to get the entire arc length when you try to calculate out with this formula. And so this becomes quite important later on in 10.4 when we start doing some other calculus with this stuff. So please take a few seconds here, guess what you would believe, what range of theta values, right? Is it 0 to 2 pi? Is it 0 to 3 pi? Is it 0 to pi? 0 to 5 pi, whatever, right? How far do we have to take this in order to get the entire curve once and only once? And while you do that, I'll drink coffee and I'll pet my cat. Hi there. Yes, good window cat. All right, I am going to transition, like I said, to my other computer as well. All right, so let's go ahead. We'll start spoiling the surprise here. So I have this first one graphed, 2 plus sine theta. And so I have it graphed, right? When I plug these things in for theta, it just graphs the entire curve. And then I also have it parametrized here. So I have r of theta times cosine. So this would be x, right? X is usually r cosine theta. And then the y's would normally be r sine theta, right? In order to just have the parameter for this, for whatever reason, Desmos doesn't like the variable theta, and so I've just included a. And so we can see here, 0 to pi, it seems to graph a pretty complete curve. It doesn't look like we have any abrupt endings or anything like this. Question is, well, can I do it with less, maybe 0 to pi? And no, right, kind of we don't have the entire curve in that case, right? So 0 to 2 pi looks like it gets it. If I take off even a little bit, so minus 0.1 or something like this, we can see that there's kind of a sliver missing here. Right? So I can't even take off a tiny little bit. And if I start to do more than this, so let's say instead of 2 pi, I do 3 pi, right? We can see that I don't really get any new parts of the curve. So it seems like 0 to 2 pi, which again is probably the natural guess for this one, does seem to be correct. So I'm going to go ahead and write that down. And we can verify just by playing this. So I'm going to go ahead, I have it mapped from 0 to 2 pi, and if I click play, we can see the point dancing around here and getting back to where it started. So, okay, yes, this seems to be correct. So let's go ahead now. I think this one was fairly guessable. Let's go ahead and graph 2 times sine of theta. So 2 times sine of theta looks like this. We can see that we have what looks like a pretty complete picture. And if I go up to 3 pi, for instance, it doesn't seem like I get any more of a picture. And if I go down to pi, we can see that we also have a pretty complete picture. So it seems like maybe we don't really need the 2 pi. And this is verified. If I go ahead here, I'd like to select this point. I thought there was a nice way. Maybe just clicking on this. So if I go 0 to 2 pi for this curve, let's go ahead and hit play. We can see that we go around twice. And so if I was to actually calculate out the arc length of this curve, right, how long is this curve? And I said, let's integrate from 0 to 2 pi, my answer would be double what it should be, right? Because I've just gone around the curve twice. And so the answer here is actually 0 to pi in this case. So 0, and we can verify if I make this pi instead, and I hit play, that we go around once, only once, and we should stop there. So the correct answer for B is 0 to pi. Okay, let's go ahead, and I took this 2, let's reset this maybe to 2 pi. These seem to be like, you know, the pretty natural guesses here. And let's see if I go ahead and I put this 2 inside. So C was R equals sine of 2 theta. So something like this. In fact, we already saw this picture. And but if I was guessing with this, the fact that we have this 2 in here, right, I know that this is periodic, right? Sine is periodic, and so I would think that going maybe 0 to pi would be enough, right? 0 to pi seems, because we're multiplying by 2, then when I'm inputting pi into this, right, we'd be getting 2 pi. And so it seems like maybe that would be enough, but actually, right, if I go ahead and I just go 0 to pi, we can see that we only have half the picture. So we actually, even though there's a 2 inside of there, and the period of that function, right, if we were just doing Cartesian, right, maybe y equals sine of 2x, for instance, the period for that would be pi, and yet we need all of 0 to 2 pi in order to get the entire curve. So the answer here is 0 to 2 pi. I guess the only thing I should probably do, right, is if I do 3 pi, we can see we don't get any more, or 4 pi, or 5 pi, right? There's no more extra pieces of the curve that I'm somehow missing. All right, so 0 to 2 pi, and again, I just really like to watch the point dance around this. Very satisfying. Okay, and then finally, one that, I don't know, even when I was looking at this, right, I got this one wrong. So this is sine of 3 theta over 2. That was part D, the final one here. Really don't know what to guess for this. Maybe, you know, 1.5 thetas or something like this. So I have 0 to 2 pi here. And we could see, like, if I drop this down to 0 to pi, we get even less. So, okay, we need 2 pi. Let's check if we go to 0 to 3 pi, right? We get even more of the curve. 0 to 4 pi, that seems like a fairly complete curve. There's no kind of abrupt endings or anything like this. Let's see if we go 0 to 5 pi. Nope, don't really get anything more here. So in this case, it's going to be 0 to 4 pi in order to get the entire curve. And let's go ahead and watch it dance around this here. So 0 to 4 pi. And here's how it gets traced out, right? As we change our theta values, it seems to be going in this clockwise direction, kind of tracing each one of these petals. Again, I would probably have guessed that it was going in the counterclockwise direction, right? Because that's normally the way that theta moves. So this one's kind of very interesting as well. 0 to 4 pi was the correct answer here. Okay, so the reason why I bring this up, because I know, right, that this, there's no way that, right, on a quiz or an exam or anything like this, that you could necessarily do this. And let me go ahead and just bring up my iPad again. But I have here at the bottom of all this, right, the message that I really wanted you to take away from this is that it's just dangerous to guess, right? Really, the only way to do this is to really graph it. And so some of these are certainly too extreme for a timed assessment like a quiz or an exam or whatnot, but really you do have to graph it in order to know kind of how far you actually need until it connects and you stop getting new points. So that's really what I wanted to bring up with this one here. And that's really the last of the kind of algebra stuff for today's topic. And again, these are just some things that I didn't have time to go over in our last class period. And they're kind of more on the conceptual or difficult side. So yeah, I wanted to make sure to bring them up here. Any questions? Or Alec, do you have anything that you would like to add before we start taking questions?
Nope, don't see any questions. And I thought you covered it.
Okay. Well, as I promised, next up is all about this calculus stuff. So calculus stuff here, so now we're getting into the tangent lines, and this one has a slightly different flavor to it, right? So we were interested in maybe when is the tangent line horizontal and when is it vertical, all this sort of stuff. And so I have this r equals 4 sine theta, right? And so I'd like to go ahead and sketch this and figure out where does it appear to have vertical tangents, where does it appear to have horizontal tangents, and then we're going to actually use that the formulas and stuff that we developed in the videos in order to verify, right, with our calculus that this, it's more than just, you know, it looks like there's a horizontal or vertical tangent there, but there actually is one. So let's go ahead. You may remember, right, we just did this. It turns out after 0 to pi, it'll be fully graphed. So let's go ahead, starting off with theta, graphing some r values, and 0 to pi will graph the entire thing, and we'll be able to see that kind of in slow-mo here as we actually graph all these things out. Let's see, pi over 2 is going to be in the middle. Let's maybe also do something like pi over 6 and pi over 3. Let's see, 2 pi over 3 here and 5 pi over 6. And if you wanted even more resolution to this picture, right, you could also do the pi over 4s. I think this is a good place to start anyway. Let's do some of the easy ones. So I think multiples of pi over 2, those are really easy to plug into sine. So for instance, if I plugged in 0 into sine, I would get out 0. Or if I plugged in pi into sine, I would get 0. If I plugged in pi over 2 into sine, I would get 1. Notice that we're multiplying by a 4 here. So 1 times 4 is going to be 4. And so already I know that if I'm looking over in the theta equals 0 direction, I need to take 0 steps off the origin. Or if I'm looking in the pi direction, I need to take 0 steps off the origin. If I'm looking in the pi over 2 direction, I need to take 4 steps off of the origin. So something like this. If I'm looking in this pi over 6 direction, well, let's go ahead and plug this into our formula here. So sine of pi over 6 would be a half. 4 times a half, that's going to be 2. So I need to take 2 steps off in this direction. If I was looking in the pi over 3 direction, so pi over 3 direction, so sine of pi over 3 is going to be root 3 over 2. So remember again that root 3 is approximately equal to 1.7. And so it looks like we're going to have 2 times that. So that's going to be around 3.4. So approximately equal to 3.4. So if I'm looking off in this pi over 3 direction, I need to do 3.4. So maybe something like this. In the 2 pi over 3 direction, it's going to be very similar. right? Sine of 2 pi over 3 is still root 3 over 2. So this is going to, again, be approximately equal to 3.4. And 5 pi over 6, plugging that into sine, that's, again, 1/2. So multiply that by 4, you're going to get 2. So again, 3.4 for this direction, and in the 5 pi over 6 direction, we need to take a step of 2 out. And so you may remember from, in fact, let me go ahead and sketch this in green. But you may remember from the pictures that we just did here that this is going to be sort of a circle that's sitting on top of the origin, looking something like this. So the two questions that I have asked here, when does it appear to have vertical tangents and when does it appear to have horizontal tangents? And I think the horizontal tangents are a little bit easier to see from this, right? Horizontal tangents, again, we're thinking about tangent lines, so things that are just barely skimming the curve. And it seems down here at the very base of the circle, it's going to have a horizontal tangent. And at the North Pole as well, at the very top of the circle, right? If we were to draw a tangent line here, it would appear to be completely horizontal. And so remember that these happened when we had like theta equals 0 was down here at the base, or theta equals pi was also down here at the very bottom of it as well. And at theta equals pi over 2, for instance, that was when we were at the very top. For the vertical tangents, it's hard to say exactly, right? Somewhere maybe around here. It doesn't, at least how I have it sketched, right? It's maybe hard to say exactly, but I would say maybe at these pi over 4s. So this is approximately where, again, the tangent line, the curve that just barely skims the circle here, that's about where it seems to be vertical. But again, maybe my sketch is off. Maybe it's really happening, you know, before this or after this. So I'm going to guess maybe theta equals pi over 4 seems like a reasonable one, and theta equals 3 pi over 4 seems to be fairly reasonable. So that's when I think that it has horizontal and vertical tangents. And now we'd like to get into actually using these formulas to help show us where these things are. So the first step is I'd like to write my polar curve as a parametrization for x and for y in terms of theta. So remember, we have x is equal to r cosine theta, and we have an equation for r, right? According to our curve here, r is supposed to be equal to 4 sine theta. So take r, multiply it by cosine, and that's what our equation for x would be. So it's 4 sine theta, cosine theta. For y, it's supposed to be r sine theta. And so, well, r is 4 sine theta. Multiply that by sine theta, because it's now the y coordinate. And if you'd like to, this one actually simplifies a little bit, right? We can make this 4 sine squared theta. So this would be the parameterization for this, for the y's. Okay, now we'd like to use this in order to verify our guesses from A. So remember, in order to get the slopes of the tangent line, this would be dy d theta on top, that's the rise stuff, and the run would be dx d theta on bottom. So we need to take the derivatives of these equations with respect to theta. So we can go ahead and do that. So if I go ahead and I take the derivative of the y stuff with respect to theta, so right now I'm looking here, 4 sine squared theta, and when I take the derivative, well, let's see, the 2 needs to come down. So I'm going to get 2, reduce my power by 1, so it's going to be sine to the first power, theta. That looks like a little prime symbol, so I'm going to get rid of this, right? But we need to reduce our power by 1, and then we multiply by the derivative of the inside. So the derivative of sine is going to be cosine. In the denominator, we need to take the derivative of the x equation with respect to theta. So here's my x equation up here, that's where I'm looking, and I need to take the derivative of this with respect to theta. So, okay, we see here that there's a product rule going on. So I need to take the derivative of the first, so I'm going to have 4 cosine theta times the second plus the first times the derivative of the second. And the derivative of cosine is going to be negative sine. And so this can be simplified down a little bit. Okay, so if this had told me, you know, find the equation, or maybe find the slope of the tangent line at particular theta values, we could now do that just by plugging these things in. And so that's what we did kind of in the pre-class video, right? We said, you know, at theta equals pi over 6, what's the slope of the tangent line? And so we could just plug this in. Here we have a slightly different question, right? We want to know when do we have a horizontal tangent and when do we have a vertical tangent? And so that's slightly different. We need to remember back from our calculus 1 days, right? Maybe again, starting with horizontal tangents. Horizontal tangents means that there is no rise, right? They have horizontal tangent lines. So no matter what the run is, no matter how far you go left and right, and kind of I have a picture right here, I might as well use it, right? As far as you go left and right, that's fine, but there is no rise. And so if there's no rise, this is the same thing as saying that in our numerator here, when is this 0, right? Because that was really the rise part. This is slope, we have rise over run, so we want to know when is our rise 0. So in order to do this, we're going to take our dy d theta and we're going to set it equal to 0. So we have 8 sine theta cosine theta, and we set that equal to 0, and we ask, well, what theta values solve this? And so we have a couple things multiplied together here. I think what this is formally called like the zero product principle, right? When you have a couple things multiplied together equaling 0, well, if either one of them is 0, that kind of does the job, right? Because 0 times anything is going to be 0. And so you could ask just individually, when does sine equal 0? Or when does cosine equal 0? And just collect all these points. So we know that sine is equal to 0, for instance, when theta equals 0, or when theta equals pi, or when theta equals 2 pi, so on and so forth. But notice that we get this all kind of sketched after pi, so maybe that's where we can end here. So that's when theta is equal to 0. When cosine, sorry, that's when sine of theta is equal to 0. When cosine of theta is equal to 0, well, that's going to be places, and again, just going back to my unit circle here, this is going to be things like theta equals pi over 2, or 3 pi over 2, or 5 pi over 2, right? Any odd power of pi divided by 2, that's going to give it to us. Also the negatives, right? We could also go backwards with all of this. But again, kind of our entire curve is sketched out after pi. So kind of I'm looking in this range from 0 to pi here. So all of these places are where we have horizontal tangents. Again, we set that rise, right? Having a horizontal tangent line, that means, well, it's like having a horizontal line, right? That there is no rise, that you can run as far as you want, but right, there shouldn't be any rise. And we're going to use the same sort of idea. I'll use a red pen for vertical lines here. For when we have our vertical tangents, right? A vertical line means that you don't have any run. You never move left or right whatsoever. You move up and down as much as you want, but you never move left or right. That wouldn't be a vertical line if you were moving left and right. And so the question is really, how do you make the run equal to 0? So again, for our tangent line, we have rise over run. So this stuff on the bottom here is supposed to be the run. And if you want it to be a horizontal line, then you don't want to have any run, right? You don't want to move left and right at all. And so for this, really, you take your run, your derivative of x with respect to theta, and you set that equal to 0. And so we take 4, let's go ahead and simplify this a little bit. 4 cosine squared theta minus 4 sine squared theta. How do we make that equal to 0? Or when is that equal to 0? Because that's going to give us a vertical line, right? That we don't have any run moving left or right. Vertical line. Okay, so again, now that we've done, right, this is really the calculus bit, right? Knowing what equations to set up. Now that we've set up this equation, we're back in algebra mode, and we just need to spend a little bit of time solving this. So maybe I could go ahead and rearrange things a little bit, and I could do, and there's a couple different ways to do this. So if you're thinking, oh, maybe I would factor this, for instance, that's also fine. There is a difference of squares here, right? And so you could certainly factor it as well. I'm going to go ahead, I'm going to divide by 4, and I'm going to move the sign to the other side. That's what I'm tempted to do anyway. And then I want to take the square root on both sides. So the square root on both sides, I'm going to get cosine equals sine. So the question is, when does cosine equal sine? And if you'd like to, you can go ahead and stop right here, right? And say, well, I know that cosine is equal to sine, right? There's a place where they're both equal to root 2 over 2, and that's at theta equals pi over 4. So theta equals pi over 4 is a fine way to go. The other way that you could do this is that I know some folks like to go ahead, right? It's in order to get down to just theta, one particular theta, we could go ahead and divide by cosine on both sides. And you could ask yourself, when does tangent of theta equal 1, right? So if I divide by cosine, right, well, cosine divided by cosine, that's the 1 on the right-hand side. And sine divided by cosine, that's the tangent on the right-hand side. And so again, this answer is the question, and you get pi over 4 is when tangent is equal to 1. And so, but I'm a little bit concerned, right? Notice that I only have pi over 4, and this is periodic. We would also have, for instance, that 5 pi over 4 would also be another solution, but that's now out of our range. But I thought there was supposed to be another answer, right? 3 pi over 4, but that hasn't appeared from this equation yet, or maybe I made a mistake. So the question is, where did I make a mistake? What did I do wrong here? What did I forget about that we need to include in order to get all the possible solutions? And yep, I start to see some answers coming in, and so far they look correct. And the answer is, right, when I took the square root, I forgot my plus and minus, right? I just took the positive square roots of everything. And so whenever you take the square root, you need to have plus or minus. And so really this turns it into like 4 different equations, right? So you could have the one that we have here. We could also have cosine of theta is equal to negative sine theta. We could have, let's see, negative cosine of theta is equal to negative sine theta. And we could have, let's see, negative cosine of theta is equal to positive sine of theta, right? And so we have 4 different equations. Luckily, though, there's some overlap, right? So for instance, this one right here, we could just go ahead and cancel these out, and we can see that that's actually the same as the original one. That's just when sine is equal to cosine. Or for these ones, right, this is basically just dividing by a negative to transfer that to the other side. So these are actually linked as well. So we don't really need all 4. Usually what I say in class and whatnot is that you need to have a plus and minus, but you only need to have 1 plus and minus, and you can choose which side it's going on. So, right, I can have the plus and minus on this side over here, right? So I have a positive sign. I already took care of that one. And you could have negative sign, or you could have it on the other side, right? Really, the choice is up to you. You'll get everything, all the solutions after 2 of these, just because the other ones are just being divided by a negative sign, essentially. So with this here, right, the question becomes, when does sine equal the negative of cosine? Right, or where, I guess really I have here, when does cosine equal the opposite, the negative, of sine? And that happens exactly when theta equals 3 pi over 4. Another way that you could go about this was, again, you could go ahead and divide by cosine on both sides. And so you could get 1 is equal to negative tangent of theta. And we could go ahead and divide by that negative sign. And we could say, when does tangent of theta equal negative 1? Again, the answer, 3 pi over 4. Right? And so all roads lead to these answers here. So at pi over 4 and 3 pi over 4, this is when I have my vertical tangents. At these multiples of pi over 2, so 0, pi over 2, pi, and again, kind of these would continue into 3 pi over 2, so on and so forth. But again, I've gotten all the solutions after this. Really, you could even argue that we don't need to include the pi for this one. That this is still mapping the exact same point here. This is when we've had all of our solutions for horizontal tangents. Any questions? Okay. So let's go ahead and move on here. I'd like to give you guys a chance to get your hands dirty a little bit here. So we'll pause for 90 seconds to 2 minutes or so. This one, it takes a while to graph all of this curve, right? But I'm interested in the tangent line when theta equals pi over 6. And so in order to get like a decent picture, right, because we want to be able to look at this and say, is our answer reasonable or not? And so with a picture, right, we can say whether the answer is reasonable. And so, but again, the entire picture would take quite a bit of time. So I'd like you to graph this picture, right, to figure out what this looks like on just the interval from 0 to pi over 3. Then figure out the equation of the tangent line. So again, we need kind of the slope of the tangent line and also an x and a y point that it's hitting, right? I need this at pi over 6. So again, please take maybe 90 seconds or so and try to get as far as you possibly can with this. Then we'll bring it back together and I'll go over the solution. All right, so this is probably where I'm going to start interrupting you. Hopefully you got through at least a start of a sketch here, and then we can do the calculus together. Of course, for those who are watching the YouTube video later, they can pause it for as long as they want and really go through all of it. But I know we only have 12 minutes left, and I do have another problem after this that I'd like to take a look at, I believe. And so why don't we go ahead and start. This is actually part of a four-leaf clover, or a four-leaf rows sort of deal here. So 0 to pi over 3, you can see actually after I did a few of them, I noticed that my picture isn't quite as good as maybe I wanted, and so I interjected a few more points. I did the pi over 12 and the pi over 4, and since we multiply by 2 when we insert it into cosine, those all end up being on the unit circle. And so this is the picture that I got as I went from 0 to pi over 3. And now we can see that here at pi over 6, right, we could go through the whole process. It looks like maybe this is horizontal, or maybe it's slightly positive. So that's kind of why we did this, just to see, you know, kind of what is a reasonable answer here. And so I think the slope of the tangent line here should be either a little bit positive, or I wouldn't be terribly disappointed, right? Maybe I just have a bad picture if it was 0. But I think it's going to be a little bit positive, or maybe a 0 for the slope of the tangent line. And so let's go ahead and figure out, right? Find the equation of the tangent line at theta equals pi over 6. So again, we need to go ahead and we need to parameterize x and y with respect to just theta. So x is normally equal to r cosine theta. And again, we have an r equation here. So I'm just going to take this 4 cosine of 2 theta and plug it in. So we have 4 cosine of 2 theta, and we need to multiply that by cosine. And likewise, y. That's usually r sine of theta. And so we go ahead, r is 4 cosine of 2 theta, and we multiply that by sine. Now we need to go ahead and take some derivatives, right? And we're going to do the whole rise over run sort of deal. So I'm going to calculate out dy d theta here, and then I'm going to divide that by dx d theta. So maybe I could even do both of these more or less at the same time. So dy d theta. So okay, taking the derivative of y with respect to theta, I'm looking over here right now, and so we need to use the product rule. So we need to take the derivative of the first. So the derivative, while 4 is along for the ride, derivative of cosine is going to be negative sine, leave the inside alone, then multiply by the derivative of the inside. So we need to have that extra 2. So that's the derivative of the first times the second plus the first, 4 cosine of 2 theta, times the derivative of the second, and the derivative of sine is cosine. So there is my derivative of y with respect to theta. Let's go ahead and do the derivative of x with respect to theta. So now I'm looking up here at my x equation, and so I take the derivative of the first, and that's going to be essentially a repeat here. So derivative of the first times the second, here we see kind of where it's different, plus the first times the derivative of the second. So the derivative of cosine is going to be negative sine. Okay, and we want to know an equation for the tangent line. Equation for the tangent line. So maybe one big thing, and really where the calculus comes into this, is the slope of the tangent line. Right, so let's go ahead and calculate out the slope of the tangent line. That's this stuff right here. This is the dy dx, the slope of the tangent line. And we need to at theta equals pi over 6. So now everywhere we see a theta, I'm going to go ahead and plug in pi over 6. So I'm going to just say at theta equals pi over 6 gives us, and again, everywhere I see a theta, I'm going to be plugging pi over 6. So let's go ahead and also clean this up a little bit. I see a 4, I see a 2, I see a negative sign, so I'm going to put negative 8. And this is just going to be sine of 2 pi over 6. That's going to be the same thing as pi over 3. Times sine of, and this one doesn't have a 2 here, that's just pi over 6, plus 4 cosine of 2 times pi over 6, that's going to be pi over 3, times cosine of pi over 6, right? That one doesn't have the 2 there. And now let's go ahead down into the denominator. Again, I see a negative 8 in total here. I see a sine of pi over 3 because I need to multiply that one by the 2. I see a cosine of just regular old pi over 6. That one doesn't have a 2 on the inside. And then I have minus 4 cosine of pi over 3 and sine of pi over 6. That one doesn't have a 2. So let's go ahead and simplify this a little bit. So I have negative 8. Sine of pi over 3 is going to be root 3 over 2. Sine of pi over 6 is going to be 1/2. Cosine of pi over 3, that's 1/2. Cosine of pi over 6, that one's the root 3 over 2. On the bottom here, we have sine of pi over 3. That's again the root 3 over 2. Cosine of pi over 6, that's also root 3 over 2. Minus 4 cosine of pi over 3, that's again 1/2. And sine of pi over 6, that's 1/2 as well. And if this is like a web work question, I think we do have something fairly similar to this in web work. You could go ahead and enter this in, but I think it'd be a little bit of a nightmare. I think maybe one more line of simplifying would kind of save you a lot of headache here. So I noticed that there's a lot of canceling that's happening, right? So the 8s and a bunch of 2s there cancel out. And so this is just going to be negative 2 root 3. There. Likewise, the halves and the 4 cancel out, and this is just going to be plus root 3 there. In the denominator here, the 8s and the 2s again cancel out quite a bit, and so we're left with negative 2. But then I also have root 3 times root 3, so that's going to be just 3 in the bottom. And then likewise, we have a lot of canceling. The 4s and the 1/2s just make this negative 1. And so we're left with negative root 3 on top, and what, negative 7 on bottom. So this is going to be root 3 over 7 if I didn't make any small mistakes. But I think this is, I did it earlier, and this looks familiar anyway. Alec, were you able to catch any mistakes during all this? I always get kind of nervous.
I didn't see any. It looks right to me.
Okay, great. Because yeah, like I said, I got this answer earlier in the day as well, but maybe I made mistakes twice. All right, so that's the slope of the tangent line, which, by the way, notice that this is a little bit positive, right? Because root 3 is around 1.7. If you divided that by 7, right? So this is certainly less than 1. So this is already kind of forming into what I thought, right, the slope of the tangent line should be. I thought it was going to be a little bit positive, right? So I'm happy with that as well. If I had gotten a negative answer, for instance, I'd be concerned and I'd really want to redo this. So that's the slope of the tangent line. Remember, the full equation of the tangent line looks like y minus some y point is equal to m times x minus some x point. And so now I know that my slope, this m value, is this √3/7. So the question is, right, in order to finish it up, I need an x value and I need a y value, right? And so this is where we actually, right, we can plug this into our old x equals r cosine theta and y equals r sine theta. And we know that theta is supposed to be pi/6, so we could plug that in. And we know the r value that's associated with this curve as well. At pi/6, we have the r value is supposed to be 2. So let's go ahead and plug these things in, and that will finish off this problem. So if I plug in r equals 2, and and theta equals pi/6, this becomes 2, and cosine of pi/6 is going to be my √3/2. So that's going to be just equal to √3. And again, r equals 2, sine of pi/6 is going to be 1/2. So this is going to be 1. So I'm going to have y minus 1, the y point, the corresponding y point at this theta value, m √3/7 times x minus the corresponding x point, which is going to be √3. And so this right here would be maybe my final answer. What is an equation of the tangent line for this curve at theta equals pi/6? So again, you can really see that the calculus bit was really for the slope of the tangent line. And that's always kind of been the case. Okay, pause for a second and see if there are any questions. Otherwise, we're going to move on because, like I said, I have another page here. We probably won't get through all of it, but we can at least start it. Going once, going twice. All right. Well, if later on you're reflecting about this and you find you have a question, right, remember you can always throw that onto Piazza and I'd be happy to answer it for you. Here I have a sketch. So this is kind of, some famous graph, kind of like a cardioid sort of deal. I think it's called a limacon, if I remember correctly. And I have a few points. I have point A. You can see it kind of down here. It's in green. I have a point B up kind of the North Pole here. And I have a point C. And so again, I have the same sort of questions that I've been asking, quite a bit today, right? Is find dy dx for these points at A, B, and C. So I have a note, right, that certainly the graph, I've given us the graphs that we can stare at it and kind of take good guesses and see what's a reasonable answer. But still, we should practice using our calculus formula in order to get the actual correct answer. So for instance, I think that at B and at C, we can see that dy dx probably, right, the slope of the tangent lines here, probably 0. I'd be very surprised if they weren't 0. On the other hand, at A, right, if I was to do an approximation, that's not super tangent, let me go ahead, cheat using technology here, something like this, I see that maybe it's around -1, but we can see that I don't really seem to go, if I was to maybe take this point down here, right, this is a run of 4, and my rise is just a little bit more than 3. Again, this is just a sketch, so it's really hard to say if this is accurate, but I mean, this is maybe like 3 point and change or something like this. So maybe it's a little bit less than -1, or sorry, a little bit closer to 0 than -1. So maybe it's around like -0.9 or something like that. So again, we can use the curve in order to kind of approximate, but we really want to use and practice using our calculus formula in order to verify. So I have this equation here. Let's go ahead and plug it in and start to find the derivatives and all this sort of stuff. So again, we need an x and a y equation parameterized just with theta. So again, normally x is going to be r cosine theta, and normally y is going to be r sine theta. But we're going to go ahead and plug in our specific r value. So 2 + 3 sine theta is our r. Multiply that by cosine. Here we have 2 + 3 sine theta is our r, and we need to multiply that by sine in order to get us our y coordinates here. Now let's go ahead and start taking derivatives. So we need to take the derivative of y with respect to theta. And so again, I'm looking here where we have just all of my thetas. If I'd like to, maybe let's go ahead and simplify this first. That maybe be nicer. I'm going to have 2 sine theta. So I'm not taking the derivative yet. I'm just expanding this out. I think it's going to be a little bit easier to take the derivative of. And likewise, I'm going to maybe awkwardly work up here. If I go ahead and expand this out, I get 2 cosine theta plus 3 sine theta cosine theta. I don't know, maybe that one's not going to be too much better. I still see that there's a product rule. I haven't really gotten rid of the product rule for that one, but maybe it'll be better. All right, taking the derivative of y with respect to theta. So I'm looking here right now. Derivative of sine is going to be cosine. Derivative of sine squared. Well, the 2 needs to come down. So 2 times 3 is going to be 6. Reduce my power by 1, then multiply by the derivative of the inside, and the derivative of sine is cosine. Next, moving on to my x's with respect to theta. So if I take the derivative of my x equation with respect to theta, so again, now I'm looking up here, my simplified x equation with just thetas in it. Let's see, the derivative of cosine is going to be negative sine. And we have a product rule. So it goes the derivative of the first times the second, so times another cosine. Well, that's just going to be cosine squared, plus the first times the derivative of the second. And the derivative of the second, well, the derivative of cosine is going to be negative sine. So let me go ahead, I have an extra sign here, so I'll do sine squared, and I'll make this negative. So there, now we've kind of fully simplified as much as we can. So we're going to go ahead, we're going to take the ratio of these, right? We need to take the ratio of these here, put them under some big fractions. We need to do the rise over the run sort of deal. But we need to know what theta values to plug in, right? So going over here, it looks like, if I was guessing anyway, when I'm looking straight up, well, I hit either B or C, but maybe it's not exactly clear. It looks like I almost hit both of them somehow, right? And so let's go ahead and plug in, right? Looking straight up, that would be at theta equals pi over 2. So if I do theta equals pi over 2, and I plug that into my equation, I'd get r is equal to 2 plus 3 and sine of theta. So sine of 3 pi over 2, that's going to be 1. So this is going to be 2 plus 3 is equal to 5. So at theta equals pi over 2, I need to take 5 steps out. You can see that that's actually the b. So b corresponds with theta equals pi over 2. So how do we get C then, is my question. And I'll wait for an answer in chat. If someone can give it to me, please. How would we get C? What theta should I plug in order to get the C point, right? When do we hit that? I like it. So I see here negative pi over 2, and that would certainly work. I like to keep my range from 0 to 2 pi if at all possible. And so I'm going to plug in its positive equivalent, right? So I'm going to plug in 3 pi over 2, but negative pi over 2 is also equally correct, just for when I post these later and whatnot. This is what I want to have written down. So either way, when you go negative pi over 2 or when you go 3 pi over 2, 270 degrees, right, this is going to be 2 plus 3 times negative 1. And so we're going to be moving backwards. So when you're looking in this negative pi over 2 direction or 3 pi over 2 direction, notice you need to go backwards by 1. So that's what gives you the C there, is that you're looking down, but you're moving backwards. So you're actually traveling up. And then lastly, in order to hit A, I'm almost certain that this is when theta equals pi, right? When we're looking in this direction, you could go ahead and verify this, but A is going to be when theta is equal to pi, right? To plug this in, we get r is equal to 2 plus 3 times 0, so that's going to be 2. So we move out in that positive direction, pi. Okay, good. So now we know what to be plugging in for these things. So let's go ahead and do for A, for instance, over here. And see, right, this is maybe the most mysterious one. So if I go ahead and I plug in pi in everywhere I see a theta, right? So I'm going to have 2 cosine of pi. Well, cosine of pi is going to be negative 1. Plus 6 sine of pi is going to be 0. Cosine of pi, again, is going to be negative 1. Divided by Let's see, -2 sine of pi is going to be 0 plus 3 cosine squared. So cosine squared, well, -1 squared here, that's going to be 1. And then we have -3, and then 0 squared is just 0. And so let's go ahead and figure this one out here. This is going to be, let's see, -2 plus 1 on top. And then in the bottom, it looks like I have 3. So this is going to be -1/3. So we can see actually my picture was, it is something, it's not quite -1, but actually mine was quite a bit off. It's not as steep as I thought it should be. And that's just because, again, this is an approximation. I'm actually kind of surprised it's that small. I would have thought it was closer to -1 though, but these things sometimes happen. And I guess I could have even simplified. I didn't even see that. I should have, that'd be another thing that I could have done, is simplified this. Okay, at B, so if I plug in theta equals pi over 2, so again, I'm looking back over here to figure out what theta value I should be plugging in for B, and then for C, it's going to be pi over 2 and 3 pi over 2. And we can see really all the action is going to be happening in the numerator here. When I plug in pi over 2 into this, what am I doing? Something's not going right here. What am I doing wrong, Alec? I'm very surprised, right? Pi over 2, this is going to give me 6 in the numerator. What have I done wrong? Oh, this is multiplication. That would do it. Sorry, I took that as addition. And in fact, that kind of helps with this as well.
That's just -2.
Yeah, and that's a lot more in line with what I was approximating, or it looked like.
Much better.
Yeah, so this is multiplication. Sorry, I looked at that there and I thought, oh, that's just being subtracted. But no, it's being multiplied. I had to go back to my original y equation right here and retake the derivative and say, made a silly mistake. Good. So now with that being multiplication there, and correctly identified as such, right, we're going to have 0 plus 6 times, who cares, times 0, right? So this is going to be 0 here, and then likewise with C, all of these cosines on the top, right? We have a lot of cosines, and cosine at pi over 2 or at 3 pi over 2, right, these are going to be 0. So who really cares what's going on in the bottom? This looks like some kind of angry person. But yes, you get 0, which is again what we were guessing with our picture back here. All right, so I know I'm 8 minutes over, so I was kind of speeding through that last bit there, but I wanted to get out the answers and just show you one more time kind of how all this is calculated out. We'll stick around for another couple minutes if there are any one-on-one questions, but otherwise, thank you so much for taking time out of your Friday to hang out with us and do some math. Again, next week, we're going to be kind of continuing through, we're going to get through the majority of chapter 10. We're going to kind of backtrack a little bit and do 8.1. This is going to be arc length. 10.2 is going to be about parametrized arc length. And we're also going to do tangent lines for parametrized equations there as well. And then 10.4, we're going to do more arc length. So it's going to be arc length galore. And we're also going to be doing areas in 10.4 as well. But that's going to, we'll start them next week, Friday, and we'll do a little bit more the following week. So again, if there are any one-on-one questions, we'll stick around. Otherwise, have a beautiful, well, it's not a bad Friday, at least not in Michigan. It was really snowing and horrible yesterday, but today is not bad. But I hope you have a wonderful day and a wonderful weekend.
See you all later.